welcome to a wide partition data modeling session in Percona Live. So we're going to explain in this session what is wide partition, or sometimes we call wide row databases, NoSQL database, and how to model your schema for such database. I want to thank Percona Live for having me. I follow this event in other occasion and the first time presenting. So thank Percona. My name is Tzach Livyatan. I'm VP Product at Scylla DB. I will explain what is Scylla DB soon. I'm using SQL and NoSQL as a user for many years, and in recent years, part of a product team and development team of such a NoSQL database. So Scylla DB is the company behind the Scylla project, a NoSQL database built for superior performance, with performance and a low latency as the focus. Scylla have API compatibility with Apache Cassandra and lately with Amazon DynamoDB. You can use Scylla as an open source project. Go to download the code, compile it if you like this kind of things, or use the closed source enterprise version with support, or like many other vendors, we also have a database as a service product, Scylla Cloud. You can see some of the users and customers that use Scylla day to day on the right. And one thing I want to mention is that the founders of Scylla was the creator of the KVM hypervisor using many clouds. So you can appreciate the fact that we are very much focused on low-level optimization and performance. And like everyone else, I'm sure we are hiring. So if you are interested in Go development, C++ development, you're welcome to contact me. So today I'm gonna start by quick introduction to NoSQL, because I'm sure most of the people on this session know what NoSQL is, at least to some extent, and then jump to wide partition data modeling. How is it different from SQL data modeling, and what partition key you should choose, what clustering key you should choose, etc. So I'll try to keep this session as practical as possible for people who are thinking or even using wide partition database already. So what is NoSQL and what is a wide partition or wide row database? So there are hundreds and hundreds of NoSQL databases out there. So it's really a very generic terms. And there are more than one dimension in which you can map this domain of NoSQL. So one popular dimension is availability versus consistency. I'm sure everyone here is familiar with the CAP theorem, which is like a crude split of databases based on availability and consistency. And I'm not going to actually touch on this talk. I'm not going to explain or not going to say how different applications you should write according to consistency. I do want to say that Scylla, Cassandra, Amazon, which are the database I'm going to mention in this talk, roughly fall into the same category of availability first. But each of them, especially DynamoDB, have a slightly different consensus algorithm. But again, it's not the topic of this call. Another way to model NoSQL database which is more relevant to this talk, is by the data model. So you can think about key value databases. I think Redis is the most popular. Document store, in which you have a key and a full document attached to it. This document can be nested. MongoDB is popular in this category. Wide column databases, or sometimes they call wide row. I call them wide partition here. I will explain later. And DynamoDB again, Cassandra, Scylla, and other fall into this category. And there are even more types of databases. There is graph database, time series database. There are more databases. So this is again a simplification. And also the line between a document store and a wide column store and a key value store is not always as clear. Some people will put Dynamo, for example, as a document because all of them have a key, sometimes called partition, and something else attached to them. So when a key value, you have just a key and a value. On a document, you have a key or a partition with a full document, nested document. And in wide partition, you have a key and a long list of rows attached to it. So we're going to touch on each of those briefly and how wide partition is different than the first two. So the main thing to keep in mind, which affect the why its data modeling on NoSQL is different than the modeling on an old-fashioned database, if you will, is the fact that NoSQL databases are distributed. Okay, so with big data and terabytes, sometimes petabytes of data, of course, not all the data can fit into one or even 10 nodes. So you might need huge clusters starting from 3 nodes to hundreds of nodes. And the database need to distribute or split the data between all of these nodes. And this split is basically, you can call it partitioning. You take the huge amount of data, try to split it into some by some key called the partition key. And the partition key basically tell you which node hold the data. Of course, each node can hold a lot of partitions, but each partition always reside in one node or a replica of this node. Also, keep in mind that Scylla and other databases support multi-data center or multi-region architecture. So not only you need to select which data center will hold the data, but also which node in this region hold the data. Now I mentioned that each partition reside in one node, but it's not accurate. Most or all NoSQL databases actually have replicas of some kind. So the data will be replicated at least 3 times in each data center and often in 2 data centers. So it can have like 6, 9, or even more replication, depending on your preference. At least in Scylla, you can choose how many replicas that you want. In other databases, it's set for you, but the principle is similar. So let's jump to data modeling. So on a very high level, the entire approach for data modeling is very different between a rational database and a NoSQL database. Again, it's a little bit crude. So on rational database, you will start with looking hard at the data itself, try to build a model that best represents the data, and then let your application choose the right query to fetch from this data. And it's hopefully you build the data or model the data in a way that every application that come along can or will fetch the data or query the data in a roughly efficient way. In NoSQL, it's completely different. The assumption here is that you cannot actually model the data, so every application that come along can query the data. So you have to do the opposite. First, you go to the application, understand which query or which reads the application need to apply, and you model the data so the application can query in an efficient way. So you're doing it in the reverse way. You need to first understand the query, then you model your data based on this query, and I will show example later. Now, as you can imagine, if you ever develop an application, this slide is quite misleading because it's present like it's a start and an end process, while in reality it's an iterative process. You think you know what your application needs, but over time, application changes, data pattern changes. So, for example, you thought you have only a few customers, but now you have billions of customers. You thought you have mostly read, now you have mostly writes. So data change, distribution change. And one of the takeaway that you can take from this session is that the data modeling is not a one-time effort. It's an iterative process. And for each application and database that you are building with NoSQL, my strong recommendation is to understand how to monitor the schema and recognize or understand when you need to change the model, when your initial assumption was wrong and now you need to change it. Because I can assure you that you will need to tweak your data modeling and schema over time. It's always the case. And if it's not the case, the reason is that your application died from some reason and it's not being used. So partition key. Partition key is the main element and the most important thing I'm going to talk about in this session. All of the databases that I mentioned earlier, key value, document data store, and wide partition, all of them have the partition key, sometimes in different name as a key concept. The partition key is a unique ID that map the data element into specific node. Again, it can be one node, it can be 3 nodes with replication, but a subset, small subset of the node in the cluster. So choosing the right partition key is very, very important. And why is it important? Because if you choose the wrong partition key, you will end up with most of the reads and most of the writes of the write of your application going to the same node. Why is it bad? Because imagine that you are investing a lot of money in having a cluster of 1,000 machine or 100 machine, and all of the reads are going to the same node, for example, X. So not only this X node will be completely overloaded and probably serve requests very, very slowly, if at all, the other hundreds of nodes are basically staying idle. So you wasted a lot of money, your cluster is super underutilized, and on top of that, you get very bad latency and performance. So, and all of that from choosing the wrong partition key. So you can imagine it's critical to try and choose the best partition key when you get it started. And before moving on, I want to take this opportunity and define a few key terms we use in Scylla for data modeling. So in a Scylla database, we have partitions. Each partition is split into rows, which can be ordered. I'll get to that later. And in each row, you have column, and the column in a row is a cell. So at least in Scylla, it's not the case in other wide row database. At least in Scylla, we have some notion of table, which is slightly different than an SQL table. And the tables have row and cell. The difference between an SQL database and Scylla, that in addition to the row cell, you have a partition that basically is a group of rows. So we'll see an example soon, but I actually want to start with a simpler example to explain the partition key concept. I want to start with a simpler example with only a partition key. So in this example, I have a primary key, which is composed only of a partition key. There is no clustering key. We'll get to that later. So imagine that I have some kind of a pet startup that try to attach sensor to a pet. In this specific table, I'm not representing the sensor data, rather I'm representing the pet ID, the owner ID, and the name. So you can find a few popular pet name here. And this is the table that I'm representing. This is on the left, you can see a SQL representation of this table. SQL, for those of you who are not familiar, is the equivalent of Apache Cassandra and other databases to SQL, which is similar in syntax, but the underlying implementation is different and sometimes confusing. But you can see that the definition of a table should be pretty similar to you. And the primary key here is the pet chip ID. Now, my question to you, is the pet chip ID a good partition key based on what I said earlier? So how would you evaluate if a partition key is good or not? So the two main motivation for a good partition key is high cardinality and even distribution. So what is high cardinality? It's very easy. High cardinality is just the number of keys that you are expecting. And when you are planning your database, you want to have as high as possible number of possible keys. So with this data modeling, I expect to have millions of pets or a billion if I'm super successful, each of them with its own ID. So it's high cardinality already, and it's a good thing. Even distribution between the partition, this is a little bit harder. So assuming that I'm inserting each pet and owner once or twice, at least right will be quite evenly distributed, but it's not exactly say that reads will be evenly distributed. So that's very much dependent on my application. So if I have a dashboard or a mobile app to see which owner is attached to which pet, I can assume that the reads will not be evenly distributed, but it's not, at least in this case, not as worse. So on most real-time application, you don't see completely even distribution. You would see something closer to Zipfian distribution, which a few of the keys getting more traffic than other. But at least if I have Zipfian, it's not as bad. The worst case that I can have, if I have very low cardinality, that I can get one partition, or imagine that I have one pet and all the reads are going to the same pet, or everyone want to see the owner of the same pet. So again, I'm getting to a hot partition use case in which I don't have even distribution and only one node or even one core in the specific node is doing all the work. So I think assuming or taking this model of a key value for my pet owner table, I think I chose a reasonable partition key with high cardinality and even distribution. Is it really the case? I need to benchmark it with some real data. I need to follow the application life cycle. And if it's not the case, change my modeling. But at least in this case, I think it's a good partition key. This is how the data will look like on disk and in memory. I have a partition that points me to a specific node, and for each partition in this specific use case, I only have one row, the owner and the pet name, so the values are here, the column name or fields are here. So this is a quite simplistic use case, but I can already use it to discuss the partition key, and here I have some rough example of what can be a good partition key and what will likely to be a bad partition key. So first of all, I'm assuming there is a lot of data. If I only have hundreds of values in my table, it doesn't really matter which key I'm choosing. It will be efficient anyway. Likely everything will fit in cache of one node. So I don't care as much. But assuming my tables will hold billions or millions of values, the partition key can be critical. So everything with high cardinality like username, user ID, a combination of a sensor ID and time, or just a sensor ID or customer, all of them seems to be a reasonable selection for a partition key. A smell or a suspect bad partition key will be something like state, age, or everything that group users into not as many groups. Because if, for example, I want to group all the people in the United States or in the world by age, you can imagine I will have a lot of users on the same age group, and as a result, a bad partition key. So how do I measure if I have a bad selection of partition key or a hot partition problem? So that's differ between databases. In this example, it's a heat map from DynamoDB. Scylla and Cassandra also have tools to try to identify what is called top partition, meaning partitions that are have more reads and have more writes. And as I mentioned earlier, it's an iterative process. You need to monitor and using this tool, try to understand if you have such a problem and then update your data modeling. So let's move, we've seen the simple example of a key value, and now I'm moving to the topic of this session of a wide partition use case. So as always with NoSQL, we will start with the queries. So in this case, I have, as I mentioned, a sensor per pet. And this sensor reports the heartbeat every second or every minute. And I want to query the database for the last heartbeat of a specific pet, or for the heartbeat of a time range of a specific pet. For example, all the result I got for a specific dog yesterday. So this is a specific requirement. Note that here, at least, I'm not trying to get the highest heart rate from all the dogs. That would require a different data modeling. In this data modeling, I'm assuming all my queries are from a specific partition, in this case, the pet chip ID, either the last value or the value between time ranges or date ranges. So the data modeling will look like that. It's similar to what we've seen before. So we have the pet chip ID, we have the owner ID, we're not using it right now. We have the timestamp and a heart rate. So for each pet, I have a lot of row in the same partition. For each timestamp, I have a different heart rate, and imagine that I'm measuring it every second. So the primary key will be composed of a partition key of a pet chip ID, similar to as we've seen before, and the ordering key or the clustering key will be time. So inside each partition, I have a lot of result for each dog. order by time. Actually, DynamoDB called this parameter, this key, ordering key. It's the same concept exactly, just in Scylla we call it clustering key. On Dynamo we call it ordering key. Both of them apply the orders of row inside one partition. So is it a good selection of a clustering key? So for the partition key, yes, I think I already convinced you that it's a reasonable column to use as a partition key in the previous session. Now the clustering key is useful if you are using a query that use this clustering key. So if I want to use a query like get me the last value, it will work because the data or the row in each partition is ordered by time, so I can easily guess the last value. It will also allow me to fetch by date very efficiently because all the rows in the partition are order. I can very quickly find a specific times in this order and do such a select. It will not allow me to do other queries. So we'll see examples soon. This is how the data will be represented. So again, we have the partition, but in this case, for each partition, we have a lot of values. How many values? Can be a lot. So imagine that each dog or each sensor report once a second. So after a year of measurement, we'll have a lot and a lot of rows inside one partition. Is it a problem? Sometimes. So some databases have limitation on how large a partition can be. On Scylla, mostly it's not a real problem because we did a lot of work for optimizing it, but it might be. So it's very much depending on your usage pattern and the value that you select. If you always select the first value and you don't care about the rest, on most cases you don't care about if the partition is large or not. If you query this row a lot, large partition might lead you to a hot partition because many of the reads will go to the same partition, and then you have a hot partition problem. So depending on your database, you try to evaluate if it's how large can a partition be, and there are ways to bypass this problem if you have it. I will show it in a second. So what will be a good clustering key? It will allow you to do useful range query and use the limit parameter efficiently. So in this case, you can, in other databases, you can choose the clustering key order. Is it ascending or descending? And you can, when you define the table, you can choose what you want, and you want to do it in a way that the limit will make sense. So if you always want to get the last value, you want one order. If you always want to get the first value, you can choose a different order. What happens if the partition become too wide? And my database started to work slower and slower because there are too many rows in one partition. So the generic way to bypass this problem or mitigate it is to add some element to the partition key. So in this case, I have a report every second, but I added the date to the partition key. This means that instead of having all the row of one specific dog in one partition, I actually split this to multiple partition per day. Partition, of course, will become much smaller, but if you want to query all the result of a specific pet, you will need to query each of the days and accumulate it yourself. So you are pushing some of the work to the application, and by that you are gaining more or better distributed partition key on the cluster. So this is a standard way to bypass the large partition problem. By the way, in some cases, you can just add a random number between 1 and 10 here, or something like that. And by that, you are forcing more distribution into the partition key, but again, you will pay for it in the complexity of your application. Last topic I want to touch today is materials view. So going back to our example, now you can look at the owner ID. And let's imagine that I want to query not just by the dog heart rate, I want to query the same information by using the owner as a key. So for example, imagine that each owner have multiple pets, like 5 dogs and 6 cats, and you want to have the highest heart rate or the last heart rate per owner from all of its pets. So on a rational database on SQL, you will just add an index, and we're actually doing something pretty similar here. So this is a query that will, if I try naively to run it, it will fail, because NoSQL database only allow you to query by a key, and here I'm trying to query by the owner. The owner is not a key. So in Scylla, you can actually bypass this by using allow filtering. Allow filtering means that you are doing a full scan of the database. So you will read all the data from all the partition and then filter it by the owner. This will work, but of course will be inefficient. How inefficient? Depends on the amount of data you have. It's still a valid option, especially for ad hoc analytics. So if you're running this query once a year, once a day, maybe you don't care, it's inefficient, and it's a valid way to do that. If you want to use this query often, for example, as part of your application, and then you want to do better, you want to add an index to it or a materials view. And this is the syntax in Scylla Cassandra to create such materials view. I'm creating a materials view with a new name on the table, on the heart rate table that we've seen before. And the partition key here is the owner. So once I created that, I can very efficiently do query by the owner. And I'm actually creating a denormalization on disk, creating another table with the same data, just with a different partition and clustering key. Now, this, of course, do have a cost. The first cost is, the major cost is in the storage, because I'm actually keeping this data twice. It's also have a cost because the database is doing the synchronization between the base table and the view for you. In some cases, you can do it by yourself. You can just add another table and insert the data there, but then you need to manage the synchronization yourself, which is sometimes not trivial. So in materials view, you can think about it as an automatic way to let the database do the synchronization for you. It's basically denormalization. And if we look under the hood, you can see that every update to the base table also translates to an update to the view. And this is actually a simplistic view, because in practice, you have replicas of each. So we have 3 replicas at least of the base table, 3 replicas of the view. So there is a lot of extra messaging going on in the cluster if you're using such a view. So you are paying for the view not only in storage, but also in messages. Read are still pretty efficient because you can go directly to the view and extract the information from there. By the way, there is another term in Scylla and other databases called secondary index. I will not cover it here, but at least in Scylla, it's a different syntax, but the implementation under the hood is pretty similar to materials view. There's some differences, but not in the scope of this session. So how will you choose an efficient index for your table? So not surprisingly, it's exactly the same rules in how you choose a partition key. So you need to choose an index with high cardinality or an even distribution, and if you don't, you will end up again with a hot partition. So if I'm adding an index, I have imagine a database of all the people in the world, and I'm adding an index by the age. Again, I will have huge number of people going to the same partition in the materials view, and that's again will probably cause a hot partition. So last but not least, what do I do if I do want to run a join between tables? I mentioned earlier it's impossible to do it natively on most NoSQL database. So in this case, you will use an external engine like Spark or Presto are 2 that we have experience with and work nicely with Scylla and other databases. But again, this comes with the cost. What this database will basically do is scan all the information, upload everything to the application, to the Spark engine, for example, and do the processing there. This tool knows how to do it in an efficient way, but still you need to read a lot of data from the database, and that takes time. So it's work for ad hoc queries and analytics, but if you do it all the time, or this is mostly what you do, maybe you need to look for alternatives. And with that, I will conclude. I only touched the surface of data modeling in NoSQL, and I try to give some practical example. I hope I succeed. If you do want to learn more, you can go to Scylla University. We have a special course on a data modeling. Most of it apply to other NoSQL databases. And if you want to contact me, I have my email here. Thanks again for Percona for having me. Thank you very much.